Good afternoon, everyone. Those of you who are following the program very closely will note that this presentation is not about zero entry mines, and I'm not from GMG. But what I'd like to talk to you today about is how to push further with 5G teleremote dosing. So this is these are insights 12 months on from a world-first deployment of 5G teleremote dosing technology that Ericsson undertook with Newmont. Very pleased to present here today on behalf of the Newmont Ericsson strategic partnership. We have a very close relationship looking at the development of cellular technology in mining, and one of the key pivots or points of that partnership has been around teleremote dosing. So just very quickly about us, Ericsson. We are one of the leading providers of ICT globally, a specialist in 5G mobile networks. We also provide enterprise equipment that sits at the edge, wireless WAN equipment, as well as private 5G cellular. Newmont, very well known amongst these halls, world's largest gold miner, operating a series of tier one assets around the world. But combined, we have shared values in terms of safety and sustainability in mining. Going back. So today we'll take a journey to Newmont Cadia. So Newmont Cadia is an underground gold mine and surface processing facility. It's around 250 kilometres due west of where we are at the moment. It's one of the world's largest gold mining facilities. It's an underground panel cave augmented by surface gold, copper and molybdenum processing. The 2025 outlook for this operation is 280 kilo ounces of production, but also produces half of New South Wales copper exports every year. A feature of the site is on-site processing, assisted with northern and southern tailing storage facilities, as well as an active pit tailing storage facility. Now, what we're going to talk about today is Newmont Cadia's tailings dam remediation project. This is, as I said before, the world's first production deployment of teleremote dosing over 5G. And what we're going to do is look at just the background, the challenges, the solution, and the scope. Now, the Newmont Cadia site is quite broad. The key features, there's a Cadia Hill pit, there's processing, there's a subsidence zone from the panel cave, but you also see here the two very large tailing storage facilities, NTSF in the blue, and in yellow, the STSF, the south storage facility. So, background. In 2018, around March 9th, the site experienced a series of earthquakes that basically resulted in a 300 metre wide degradation of the northern tailings facility wall. Luckily, the degradation resulted in a loss of containment that was held within the basin of the southern tailing storage facility capability, and due to timely activation of the site's dam safety emergency plan, there was no injury or loss of life. So basically, what we're left with at the end of the day was a 300 metre wide hole in a wall, but no major injuries. Now, there were some underlying geomechanical factors at play with here. As I mentioned, there were the earthquakes the day before, but I won't go into the details of the 120-page report that was prepared for the Independent Technical Advisory Board, but generally what we saw in results was that the foundation of the dam wall was slipping. They were moving forward gradually, so the wall was moving forward, causing cracking. But the other factor the day before was those two earthquakes caused vibrations in the liquidized and the waterlogged slurry, liquefying it, placing extra pressure at the upper levels of that 90 metre high structure. Just to give you some context, this tailing storage facility is 4 kilometres wide, 90 metres high. So when you get liquefaction of those tailings at a somewhat higher level, it's putting undue stress on the top of the wall. And you can see here on the left the cracks that were found that morning of March 9 in, I think, stage 8, which is around 80 metres off of ground elevation. So, how do you fix a 300 metre wide hole in a 4 kilometre wide, 90 metre high structure? Whoop. I was just talking about pictures and you had no idea what I was talking about. So you can see here on the left the cracks at stage 8, 80 metres high. So not the sort of thing you want to see in a tailings facility wall. And you can see the geomechanical breakdown from the Independent Technology Report. So the way they resolved this was to moved into place stabilizing buttresses. Now, this involved moving around 8.5 million cubic meters of earth in a short space of time. Now, that's a big number. You're probably wondering what is 8.5 million cubic meters? For those fans of cricket or AFL football, that's enough earth to fill the MCG to the top of the third tier 6 times over. This is an international mining conference, so I have to translate things into international speak. If you're a fan of the world game, soccer, that's enough to fill Wembley to the roof 7 times over. So a lot of earth to move in a short space of time. So how do they do this? What were the challenges? So challenge number 1 was a low factor of safety. We were dealing with a fundamentally weakened dam wall. And under the Australian National Council for Large Dams guidelines, there are safety standards that apply for works in that sort of environment. And what Newmont actually found was the factor of safety that was applying for any work in front of that dam wall was below 1.3, which under the guidelines means that it cannot be any manned equipment at any period of time. So to move this earth, they need to use remote controlled equipment, remote controlled dozers to move this into place. Second issue, limited time. You can't run a gold processing facility if you don't have anywhere for the tailings to go. So processing stopped at site for an extended period. Site reconfigured itself to make use of the Cadia Hill mined out pit, and it became the new pit tailings storage facility. But as a pit, there was limited storage capability. And as you can see from these photos, it's refilling reasonably rapidly. On the left, September 2018, just before it was starting to be filled, relatively empty. In the middle, December 2021, it's filling up, and just about a month ago, 2 months ago, it's running out of space. So there had to be time was of the essence. The third challenge was around wireless performance requirements. The teleremote systems they were using on their dozer fleet were pretty demanding in terms of wireless connectivity. Each dozer required over 6 megabits per second uplink for all the video streams that were being pushed in the network. It required 50 milliseconds worth of performance, responsiveness, otherwise auto stops would be triggered. It could not exist and operate with more than 1.5 seconds disconnect from the network, and required less than 2 packets to be lost before an auto break or e-stop would be triggered. This caused a slight little problem because what we had with a target of 16 machines required to move the 8.5 million cubic meters in the time frame, there were 64 cameras total. And those 64 cameras basically amounted to 132 megabits per second of data that had to be streamed across the network. And here was the problem. What wireless technologies did Newmont have at their fingertips? Wi-Fi that they had been using could only support 2 dozers. They added the third and everything stopped. The requirements of the teleremote application exceeded the capabilities of the Wi-Fi technology that was deployed at site. They looked at using 5 gigahertz Wi-Fi, except it was already being used for backhaul of the 2.4 gigahertz Wi-Fi, so that wasn't an option. They looked at proprietary technologies, just not Wi-Fi. But the problem there is 5 gigahertz, doesn't matter whether it's use of Wi-Fi or any other technology, wasn't available. They also looked at whether they could leverage their private 4G network on site, but even on the best day with the wind blowing in the right direction, there wasn't enough capacity in that 4G network. So the only way they could actually achieve the outcome with the size of fleet they needed was with 5G technology. The fourth challenge was around fundamental Wi-Fi technology issues. So using Wi-Fi, the dozer slots were limited to 100 metres, which meant that the work across this 4-kilometre wide facility was being arranged in 4-day work packages of 100 metres at a time. It meant that if the dozers pushed past 100 metres, the network became unreliable, which was an impact on productivity. It also meant that the factor of safety line that earmarked where human operation could apply versus teleremote operation had to be moved regularly. And each time the Wi-Fi network moved was a loss of productivity of at least 1 to 2 hours, notwithstanding extra troubleshooting time. There was also connection instabilities. So there was a line of sight dependence. Newmont found when they were operating the dozers that if they lost line of sight to the Wi-Fi infrastructure, the dozers stopped, had to be restarted. There was the unpredictability of weather. They would lose connectivity if it rained, if the wind blew a particular direction, if it was cloudy. Now, those of you with a technology bent were thinking, that doesn't make sense. But the actuals were there. The network became unreliable every day it was cloudy and often spent more time troubleshooting the network than pushing Earth. There were random black holes, unexplainable. Dozers would just suddenly fall off the network, no reason why. If they changed the angle of the dozer, it would fall off the network. The camera feeds would be lost near the edge, just at the time they were pushing over the edge. The operators did not want to lose visibility and control of the machine at the most precarious stage of the push. And finally, and this is the most frustrating thing for the operators, outages could take up to 6 hours to resolve. So if you're there on site trying to push Earth for 10 to 12 hours, and you have to spend 6 of it chasing down problems with your connectivity, major problems. So the solution, 5G was the answer. So through a consumer lens, 5G is a technology that promises 10 to 100 times speed increase, 1,000 times more devices, 5 times improvement in performance, a 5 times reduction in power consumption. But for mining, and particularly in the Newmont case, it provides a series of benefits over Wi-Fi and extend the capability of what Newmont had on site with 4G. It gave us licensed spectrum security, improved coverage and reliability, increased uplink performance, increased reliability, and lower latency. We'll talk about what these really mean. 5G new radio technologies, though, were absolutely fundamental here. So 5G for dozing gave Newmont more access to spectrum. Radio spectrum is critical for cellular networks. With this, they had more capacity. With 5G new radio technologies, they'll get more upload speed. So where we're talking around 132 megabits per second, 5G was the only technology that could achieve those levels of performance. But then the new 5G radio technologies also gave us extended range. With advanced antenna systems and massive MIMO, we're able to generate 10 times performance of a regular mobile network in the uplink, which was used. We're also able to reuse the spectrum that was available at site by a factor of 3. So massive changes here in how this technology could apply. Now, to give you an idea of what this technology means, it's like walking to a room, turning the light on, you get the room's lit up. With this advanced antenna technology and with 5G, it's like taking a bright light, a bright torch, and shining it out there. We're focusing the radio power, we're focusing the radio energy, so it shoots further, shoots longer. That's the key here. So where you normally only get a kilometre range out of this type of technology, we're able to achieve 3 kilometres. So the 5G teleremote dozing that was deployed at site, not really that complex in terms of the number of parts. There was the Ericsson private 5G platform that included a core sitting in the remote operations centre. There was a single radio sitting on a mast covering the NTSF facility. And then there were specialist mining grade CPE deployed on each of the dozers. All this was covered under an SLA-backed monitoring service that Ericsson provided to Newmont to ensure that the system was running when they needed it and that the 5G network wasn't the same productivity drain that the Wi-Fi network was. In terms of coverage and performance, you can see on this diagram here the coverage we got out of it. A single antenna covering across the face of the dam wall would help us project and connect dozers up to 2.8 kilometres away. So you can imagine now the impact to the operators. Where previously they could only operate with 100 metres of their infrastructure, now they could operate dozers 2.8 kilometres away without any degradation in performance. So the outcome. Many things that came out of this, from the Newmont side and from the human side with the operators. So Newmont saw a 50% increase in productivity simply by turning 5G on and being able to add more dozer equipment. They were able to achieve the fleet ambitions that were holding them back. There was the extension of the operational range, as I said before, limited to 100 metres. Now they will operate up to 3,000 metres, and at the same time achieve the uplink speeds that were fundamentally critical to their dozer application. They were able to shift more than 25% more material per shift, which meant that from a productivity standpoint, the bottleneck was no longer the productivity of the dozers, the productivity impact was the trucks feeding the dozers. Finally, the whole thing was able to provide simplified management performance, meaning that Newmont didn't need to have network engineers on site to be able to maintain and operate this network. The dozer operators were ultimately able to do that themselves, all through the simplicity. From the dozer operator perspective, what were the people meant to be in the cabs saying about this technology? Fewer dropouts and disconnects meant they could have longer continuous operation with fewer mental headaches. They had improved machine safety. So the big concern that these operators had is they were responsible for the machines. They made the decision at the point of the tip head. Do they keep pushing if the cameras failed, or do they stop and take the productivity hit? With this, the cameras didn't fail, so they had that full visibility. As they were moving, they had full situational awareness of rocks and seeing whether they'll be causing damage to their torque converters. There's operator well-being. We don't think about this a lot, but mental health was top of mind for these operators. They were frustrated by turning up to each shift and having to spend the entire time trying to troubleshoot why this network wasn't working and they couldn't be pushing. The feedback that they gave us from this is they are now spending more time pushing dirt rather than chasing signal. Huge benefit for their mental well-being and reduction of frustration. Finally, what they did see was a more natural experience. It was noticeable, the improved responsiveness from joystick to dozer. Historically, these operators have to go an extensive retraining, readjustment process to be able to move from being in the cab with a touch and feel experience of the dozer to having a remote control experience. The operators were able to actually notice a faster response, action to dozer response improved dramatically with 5G. And for them, they actually realized that it meant that bringing new operators in was going to be a much easier prospect for them. So finally, the future is more. So as far as Newmont's concerned, this has been a resounding success. They saw that with this technology, they can deploy at greater scale at this site, but also into other sites. The benefit of 5G, though, is open their eyes to where the technology could go. So there's options here for control to be moved away from the actual tailings dam to admin block. In fact, the operators are asking, why do they need to go site? With 5G connectivity and the reliability, couldn't they just operate from a hub? Or in one of the cases, the operator is saying, why go to Orange? I live in Newcastle, I'll operate from Newcastle. High fidelity audio. A lot of these remote control experiences are governed by the operators being able to see what's happening around the machine, but also feel the vibration and hear what the machine is doing. So the view here is with 5G and with high capacity, why can't we move to 4K and 8K Ultra HD sort of video for an immersive experience? Why can't we hear hi-fi quality audio to really hear what the machine is doing? And then ultimately, science fiction prevails. Can we get haptic feedback? So what the dozer is feeling through the blade can come back through the joysticks via remote control. Newmont just isn't stopping here at Orange though with the remote control dozers. The project continues today. The dozers continue to push. What they're doing though is they're taking the same success of this technology and they're replicating it to their other mines. So today there is a similar network with more radios sitting at Newmont's Boddington mine where they're connecting 16 autonomous drills, and they're planning on extending to other sites globally. So with that, thank you very much for your time this afternoon. I hope you enjoyed hearing about the Newmont experience with 5G dozer push. If you'd like to learn more, you can scan the QR code there or visit the link, and you'll be able to download a case study outlining the experience and the lessons and insights from Newmont. So with that, thank you very much.